Hey everyone, and welcome. Today, we're jumping into something that's like the secret language of mathematics. It's a way of thinking that helps us group, organize, and just make sense of the world around us. Yep, we are talking all about set theory. So, to get our brains warmed up, I've got a question for you. Picture all the colors in a rainbow. Got it? Okay. Now picture the starting five on a basketball team. I mean, they seem totally unrelated, right? But believe it or not, from a mathematical point of view, they have something huge in common. Any ideas what that might be? And the answer is, they are both perfect examples of a set. That's it. They're just distinct collections of things. And this simple idea of a set is exactly what we're going to unpack today. Trust me, it's a concept that starts simple, but has some seriously powerful applications. So here's our game plan. First, we're going to nail down what a set actually is. Then we'll learn the lingo, how to talk about them. After that, we'll meet all the different types of sets. And finally, we'll get to the fun part, seeing what we can actually do with them. All right, let's dive right into part one. What is a set? Seriously, this is the absolute core concept. Everything else we talk about today is going to be built right on top of this foundation. Okay, so here's the textbook definition. A set is a well-defined collection of distinct objects. And those objects floating around inside the set, they get a special name. We call them elements or members. Now, there are two really important words here, distinct and well-defined. Distinct is easy. It just means no repeats. But what in the world does well-defined mean? This is so important. Well-defined just means there's zero ambiguity. We have to know for sure if something belongs in the set or not. Take the collection of vowels. That's a set. Why? Because we can all agree on what A, E, I, O, and U are. No debate. But what about the collection of good students? Well, that is not a set. My idea of a good student might be totally different from yours. It's subjective. Same thing for beautiful flowers. There's just no clear rule. Okay, so we know what a set is. Let's move on to section 2. Now we get to learn the language, the actual notation we use to write and talk about sets. It's kind of like learning the grammar for this whole new mathematical world. Turns out there are three main ways to do this. First, there's the descriptive form, which is exactly what it sounds like. You just use words. Second is the roster form, where you literally list out all the elements. And third, we have the super powerful set builder form, which is all about defining a set by telling us the rule its elements have to follow. Let's see this in action. On the left, we've got the roster form. See the curly braces with A, E, I, O, U listed inside? Classic. On the right, it's the very same set, but in descriptive form, the set of vowels in the English alphabet. See? Two different ways of saying the exact same thing. Now, listing stuff out is great for small sets, but what are you going to do if the set is infinite, like, say, all the positive numbers? Or what if the elements follow a really specific, complex rule? You can't just list them all. You'd be there forever. And that is where our third method comes in to save the day. This right here is our look at the amazing set builder notation. Let's break it down real quick. The curly braces still just mean the set of. The X you see is just a placeholder, a variable for any element in the set. That vertical line, that means such that. And then everything after that line is the rule. So you'd read this out loud as the set of all elements X such that X is greater than 0. It's a ridiculously efficient way to describe massive or complicated sets. All right, on to section 3. We can define sets, we can write them out. Now let's meet the different kinds of sets out there. I kind of like to think of them as a family where each member has its own little personality. So first up, you've got the empty set, which, yep, has nothing in it. Then there's the singleton set, which is a little lonely. It has exactly one element. A finite set is one you could eventually count, even if it's a huge number. And its opposite, of course, is the infinite set, which just goes on forever, like the set of all numbers. And finally, the big boss, the universal set. Think of it as the container that holds all the elements we care about for a specific problem. And this visual is just perfect for understanding this. That big outer shape, that's our universal set. In this case, all complex numbers. But look inside. We can see how the set of counting numbers fits completely inside the set of whole numbers, which fits inside the integers, and so on. This is a beautiful illustration of a subset. Each smaller circle is a subset of the one it's inside. So cool! Okay, for our last section, it's time to put these sets to work. This is where we learn about operations, the things we can actually do with sets to smash them together or figure out what they have in common. This is where the magic happens. Our first big operation is the union, and it's represented by that U-looking symbol. The easiest way to think about it is uniting. The union of two sets is just a new, bigger set that contains every single element from both of the original sets you started with. Check out this simple example. If set A is 1, 2, 3, and set B is 3, 4, 5, their union, A union B, is 1, 2, 3, 4, 5. But, and this is important, notice how the number 3 is only listed once. Even though it was in both sets, we only write it down one time in the union. Remember, sets are all about distinct, unique elements. And our second key operation is the intersection, which looks like an upside-down U. Now, if union is about combining everything, intersection is way pickier. It's only about what's shared. The intersection is the set of elements that are in both set A and set B at the same time. So, using those same two sets from before, what's the one and only element they have in common? It's just the number 3, right? So the intersection of A and B is simply the set containing only 3. Easy peasy. Okay, let's bring this into the real world. This Venn diagram is showing us some info about passengers on a flight. The circle on the left, which is labeled H, represents everyone who's on holiday, and the circle on the right, labeled C, represents everyone who hired a car. All right, take a close look. How many passengers are on holiday and also hired a car? Remember, that little word "and" is our big clue. We're looking for the intersection, that sweet spot right in the middle. And there's our answer, 150. You can see that number sitting right in the overlapping area of the two circles. That's the intersection of set H and set C. It's the group of people who are members of both sets. So let's do a super quick recap of the essentials. First, a set is just a well-defined group of unique things. We know we can write them out with words, lists, or rules. We met the whole family of sets, from empty to infinite. And we learned how to use operations, union to combine everything, and intersection to find only what's shared. Okay, before you go, I want to leave you with a thought. Think about your music streaming app. It knows the set of songs you've liked. It knows the set of artists your friends listen to. It probably even knows the set of songs that are popular in your city. How could it use unions and intersections of all those different sets to create that perfect Discover Weekly playlist just for you? It's a pretty cool idea, and it's all built on the simple building blocks we covered today.